The purpose of the Born-Haber cycle is to calculate the lattice enthalpy for the formation of an ionic compound. So in this example, we're going to calculate the enthalpy change when lithium ion plus fluoride ion become lithium fluoride solid. Now, the Born-Haber cycle is really an application of Hess's law, but sometimes we represent it graphically. So I'll show you that here, and then I'll show you the Hess's law version. So for our graphical version, we can start by drawing a line for lithium fluoride as a solid. Now, we know that we want to make that lithium fluoride from lithium plus in the gas phase and fluoride in the gas phase. And so the energy difference between those two things is going to be delta H of our crystal, our lattice enthalpy. Okay, and so the lithium and the fluoride are our reactants, and lithium fluoride solid is our product. Now, we can use a whole bunch of other quantities that we know in order to get our lithium in the gas phase and our fluoride in the gas phase. So one other quantity you might know is the heat of formation. So if we take lithium solid and half of a fluorine in the gas phase, so the elemental forms, and we make lithium fluoride, then that is going to be the delta H of formation. Okay, well, so that gets us lithium solid and half of a fluorine gas. But so we need to basically convert both of those things into their ion forms. So let's sort of start with lithium and pull it through. So for lithium, in order to make that a gaseous ion, we first need to make it a gas. So we can imagine lithium gas plus half of our fluoride. And that energy change is going to be the heat of sublimation. So sublimation taking a solid and forming a gas. Okay, and that's a quantity we could know. Then the other thing we need to do is make it an ion. So we'll add the ionization energy, lithium plus as a gas, plus half of a fluorine gas. And so that energy difference is going to be the ionization energy, which I will sometimes abbreviate just IE, ionization energy. Okay, so another thing that we can know, like another quantity, so we've kind of gotten lithium under control, but the last thing we need to do is get fluorine to where it's supposed to be. So we can make that fluorine, half of a fluorine gas, into fluorine atoms. So we're keeping our lithium the same, and we're going to dissociate that bond so that we get just fluorine atom. Okay, so that is going to be half of the bond dissociation energy of fluorine. So we've broken the fluorine in half. And then finally, the last thing we need to do is turn that the lithium and the fluorine into turn the fluorine into fluorine ion. And so when you have that fluorine plus the electron that came from lithium, that energy difference is the electron affinity. And we know the electron affinity of fluoride, or at least something we can look up. Okay, so we see that this forms kind of a circle or a cycle, hence the name Born-Haber cycle. Maybe you can also see that a lot of these arrows point up, but some of them point down. And so because of that, that's going to affect the sign of these things when we go to calculate it. So if we put all of this together, we will see that the lattice energy is going to equal the heat of formation minus the heat of sublimation minus the ionization energy minus half of the bond dissociation energy minus the electron affinity. Okay, So let's see how this plays out in Hess's law so that you can understand why the signs are the way that they are. So the reaction that we're going to start with is the hetoformation. So imagine we have lithium solid and half of an elemental fluorine gas, and we're going to make lithium fluoride solid. So that is the hetoformation, the delta H for that reaction. Okay, now I want to turn that lithium solid into lithium gas, but ultimately I'm going to want the lithium gas as a reactant to get to my enthalpy of my lattice enthalpy reaction. So I'm going to make the lithium gas the reactant so that it will cancel with lithium gas, the reactant in the first reaction. And so that's going to be negative the heat of sublimation because it's the reverse direction. Okay, same idea where I'm going to want lithium ion from lithium solid. And so that's going to be the opposite of the ionization energy. All right, so I've got the lithium ion. Now I'm going to need to deal with fluorine. So for fluorine, I want half of the energy that it takes of the reverse of the energy it takes to split fluorine gas into 2 fluorine atoms. So that is going to be negative 1/2 of the bond dissociation energy. And then finally, I want to end up with fluoride ion as a reactant. So I have gaseous fluoride ion goes to a fluorine atom plus an electron. And so we see that that's the opposite of the electron affinity. So if I add up all of those reactions and cancel out all of the things that appear on both sides, then I end up with lithium ion in the gas phase plus fluoride ion in the gas phase becomes lithium fluoride solid. And so then delta H of that reaction will be our lattice enthalpy. Okay, so now that we kind of see where this comes from, then we can actually add up these numbers. So I have found these numbers in the back of a Gen Chem textbook or from NIST on the website, or there's an appendix that goes with our textbook. And so we can find these numbers. They come from experiments that people have done. And so here, if we add them all up, we see that the heat of formation is negative 618 kilojoules per mole minus the heat of sublimation, which we said is 161, minus half of the bond dissociation energy, which is 158, minus the ionization energy. Oh, we're kind of out of order here. The ionization energy is 520. Let's fix that. Okay, let's do ionization energy, which is 520. Then half of the bond dissociation energy, which once again we said is 158, minus the electron affinity, which is negative 328. All right, so if we do the arithmetic there, we get that the lattice enthalpy is negative 1050 kilojoules per mole. Okay, so what does that number actually mean? That number is a pretty big number for lattice energy, which is a testament to the fact that both lithium and fluoride are really unhappy as gaseous ions and would really prefer to be in the more stable environment of a crystal lattice. We also see that that's a really big reaction for a chemical reaction. So this is a really exothermic reaction. In the next couple slides, we'll start to compare this number to numbers that we can get theoretically, and we'll see what that tells us about the bonding in lithium fluoride.